Welcome, and thanks for joining us. My guest today is Dr. Kathleen Fisher, Director of the Information Innovation Office at DARPA. Dr. Fisher, thank you for joining us.
My pleasure. Happy to be here.
And just before we get started here, could you give us a little bit of an understanding of what DARPA does and what the Information Innovation Office does?
Sure. DARPA's mission is detecting and creating strategic surprise, so looking over the horizon for opportunities and threats that might be coming and creating technology to take advantage of the opportunities and ward off the threats so that we're well prepared for what might be coming as a nation.
All right.
And the Information Innovation Office is charged with doing that in the information space, so computer science broadly construed.
All right. Well, thanks for giving us a little bit of an understanding of both DARPA and the office there. We're obviously talking about all things artificial intelligence today and how that is a fast-moving front in the federal government. So just to frame the conversation in more concrete terms here, what are some of the use cases that AI that DARPA is putting into use these days, and how are those use cases helping DARPA meet its mission of strategic surprise?
Yeah, so use cases of AI is pretty much the entirety of DARPA's mission. So something like 70% of DARPA's efforts involve artificial intelligence in one way or another. So in the information space, we are looking at using artificial intelligence in many of the things we do. So one example is the CASTLE program, which is looking at using artificial intelligence to better defend our systems from cyber attack. So of course, in addition to AI being everywhere, cyber attacks, ransomware, things like that are another thing that we are seeing increasing levels of. And the common practice for when a system is the victim of a cyber attack is to take the system offline and then go and find all the places where there's an attacking code and clean the system and then put it back online. But that taking the system offline is another way that the attacker is attacking the system, because now you have a denial of service attack where the legitimate owners of the system can't use the system, which is bad. It's bad for normal practice, but it's also bad for military, national security kinds of applications. So the idea behind the CASTLE program is, can we defend the system in a different way? Can we have a cyber agent that can actively defend the system while it's under attack using a kind of AI called reinforcement learning? Can we train active defenders? And the way we train those active defenders is to have active defender, which is a kind of cyber agent, and an active attacker that is mimicking the actions of an attacker, and they kind of attack each other or play off each other in a cyber gym. Where the attacker pretends to be a bad guy and the defender is a good guy, and they learn how to attack and defend to be able to protect the system while it's under attack. So that's one example. Mm-hmm. Another example is in the Provers program. And here, this is part of our resilient systems portfolio. And the premise of the resilient systems portfolio is, can we learn how to build our systems so that they are much less vulnerable to attack? So those malware, ransomware systems have a much harder time breaking in and taking over control of our system in the first place, so that we don't need the CASTLE program. And one of the capabilities, or the key pieces of technology that enables that, is something called formal methods, which is mathematical techniques to allow us to build software that is provably correct, though it's guaranteed to do what it's supposed to, and critically not do what it's not supposed to. And if it's guaranteed to not do what it's not supposed to, then the attackers have a much harder time getting that initial hold onto the software. The challenge is that building software and proving that it's not going to do what it's not supposed to is much harder to do. It takes extra levels of skills. And so Provers is about building tools to make that easier to do, and that making it easier to do uses AI-based technology to automatically build proofs that the code is doing what it's supposed to. And then when you have a proof and you make a change to the code, can we automatically update the software so that you don't have to go and redo the proof? The AI system redoes the proof for you. I have more if you want me to keep going, or I could stop there and you can ask another question.
No, I think that's incredible, because I think the whole value proposition is that both the speed and scale of that in today's world, the threats are coming harder and faster than ever, and the AI can scale up to meet those challenges. If you have more use cases, I'd love to hear them.
Yeah, sure. Yeah, so you're exactly right that what AI is going to let us do is basically speed and do things faster and at bigger scale, which is critically important because the world is faster, bigger scale, more systems. So another use case is in the LINK program. So here we have, its focus is on control systems. There are many vehicles, for example, that are controlled by software that is relatively simple control system code. So like think of a Humvee that has, you think you're driving it by yourself, but in fact there's lots of code that is helping you stabilize, helping soldiers stabilize the vehicles, that is taking data from sensors and controlling actuators that are controlling the vehicle. Humvees are pretty much not stable because they ship from the factory in one configuration, but then we add all sorts of equipment onto the top that makes it kind of top heavy, which makes it easy for those vehicles to tip over because the sort of dynamics of the system have changed from the original design system. So the premise of the LINK program was, can we use machine learning to study the data of the system and learn the new control dynamics of the system, either when it's augmented in that case or when it's damaged. Like if you have a little PackBot robot, if the treads become damaged or they don't function the way that they were originally intended. When this program was originally pitched, people who are experts in control systems like, that's crazy, that's never going to work, which is kind of like the sweet spot of a DARPA program when no, that's never going to work. So like the original metrics were made much easier because that's not going to work. You can't do that. And the program manager originally suggested that they would just need a small computer, like a kind of computer that could run on a cell phone. No, you're going to need a supercomputer, like a really big computer to do that. And the program manager's like, okay, you can give me more compute and you can give me lower metrics. But what he showed was in fact that his original concept was indeed true, that you could study the dynamics in the control system and have it automatically notice when the system was damaged, how to change how the system is being controlled to automatically adapt to the new configuration of the system and change. So that right now this is it's a basic research program. So we're not actually working on Humvees yet. We're working on PackBots, little robots. But we think that the technology will translate into things like Humvees. So they're working in a robot test ground with PackBots where they degrade the functioning of the treads and watch how quickly the system is able to notice that the treads aren't working and adjust. And the answer is in so fast that you can't even tell. You think that if you're driving it via a remote control handheld thing, and you think you've just become really good at driving it, but in fact it's adjusted to figure out to the change in the configuration. Another test was it was driving up this slope and had a big sail on it, and it had much higher wind conditions than they were expecting. And it was driving up the slope and it started to slide back and then go forward and slide back, and they thought that the system was broken and that they were just about to take it down, and they realized that the system had learned how to tack from sailing. And so the program manager is super excited about how much promise this program is showing in having machine learning be able to monitor the performance of relatively simple control systems in the presence of degradation of the system or changes in the configuration of the system, like adding the water tanks and things like that, to be able to rapidly adjust. An example application would be the Evergrande in the Suez Canal is an example of a system that has relatively simple control systems that ran aground when the wind conditions became. So they've been doing similar examples like that in the Charles River in Boston, and this technology would have prevented that kind of an accident happening. So that's another example of using machine learning and AI capabilities to sort of work magic. Anyway, so that's an example.
Wow. Well, Dr. Fisher, thank you for going deep on all those use cases. I think a question we've been trying to answer with this series is, where is the future of AI? But based on what you've just said, the future is already here in a lot of regards. I wanted to shift gears a little bit and talk about the administration's executive order on artificial intelligence. Obviously, that is in recognition that some agencies are lower in this learning curve with AI than DARPA, which is by its mission, on the leading edge of this technology. But I wanted to ask you anyway, in terms of that AI executive order and what it does in terms of a demand signal from the administration, what does it elevate or what does it prioritize for DARPA that it perhaps may not have been doing before or now needs to emphasize given that EO?
Yeah, so the EO is all about making sure that AI is being developed in a way that is well aligned with the needs of society, the needs of the country, the needs of national security. And DARPA's mission is making sure that we are advancing what's needed for national security, for the country, et cetera. So DARPA's goals and missions are well aligned with the executive order. So some of the things that DARPA has been working on are explicitly called out in the executive order. So some of the priorities DARPA is working on are, for example, the Semaphore program, which is about detecting manipulated media. So DARPA has been working on Semaphore for 4 years, and that was a follow-on program to the Metaphor program, which was also about detecting manipulated media. So this is a thing that DARPA has been worried about for quite a long time. The Semaphore program has had some quite impressive results in detecting manipulated media. The idea is often to be able to find inconsistencies that, kind of like when police interrogations, right? You put two people in a room and you find out where they're not consistent. So you don't necessarily know which one of them is lying, but you know one of them is lying. So like in media collections, if you can find where they're not consistent with each other, you know that they can't both be true. So one of the parts of Semaphore is in looking at when leaders are talking, when people talk, when I'm talking, I have micro expressions where when I say the word hello, maybe I always raise the space over my eyebrow. Like we all have these micro expressions that are characteristic of how we speak, and we can use machine learning again to train person of interest models that capture those characteristic micro expressions. And it used to take about 10 hours of video, and now it's shortened down to about an hour and a half, I believe, of videos. And we can build those defensive models so that when a purported message comes out from a person of interest, we can compare the purported message with that defensive model and see, like, are those micro expressions present? And if not, we can demonstrate that here's the purported video, here's the expected micro expressions, here's where they're not. So that even a layperson can see, like, here's what's expected, here it's not there, in a very fast response time, so that you don't have to trust the expert. You can, like, look, here it's not there. So that's an example of the kind of technology that has been developed on the Semaphore program that is consistent with what's in the executive order. The executive order, and legislation from Congress is directing the Commerce Department to go and push this kind of technology out into industry so that it's available on a commercial basis, so that there's a mechanism for people to have trust in what's real and what's not real. Also working on watermarking kind of technology to, like, is this authentic back to the sensors that created the image, or is this more generated from large language models, et cetera. So that's one aspect. So manipulated media, what can you trust, what can you not trust? Another aspect is the AICC program. So this has to do with automatically finding and fixing vulnerabilities in open source software at speed and scale. So last year, Avril Haines testified to Congress in February that in the event that China were to invade Taiwan, it's very likely they would carry out destructive cyber attacks on US civilian infrastructure in advance of that attack. And furthermore, that it's very likely that they would have the capability of carrying out such destructive attacks. That is consistent with testimony that Nakasone and the head of the FBI and Jennifer Easley and Coker testified before the Select Committee on the CCP gave, that basically said that Microsoft called it the Volt Typhoon effort, which is placing destructive cyberware on US civilian infrastructure, not with the intent of espionage, not with the intent of stealing industrial information, but with the intent of basically placing bombs on, again, US civilian infrastructure in the event of invading Taiwan. So how do we counter that effort? And fixing bugs in open source software at speed and scale is one way of dramatically reducing our attack surface. With AI is again, you talked about AI being the speed and scale multiplier, right? So AICC is our effort to do that. It's an open competition. It was announced at Black Hat last August. The semifinal competition will be at DEF CON this August. The finals will be at DEF CON next August. That's an extremely fast, very aggressive timeline, because that's what's appropriate for that threat timeline. We are partnering with OpenAI, Google, Anthropic, and Microsoft. They will be providing access to their frontier scale models, large language models, with the goal of finding and fixing those bugs at speed and scale. We don't know if it will be successful, right? DARPA does high risk, high reward research, so it's possible that it won't be. But the preliminary, like what's available in academic papers so far, suggests that the technology shows promise. So that's again consistent with the executive order. And then a third thing is, how do we understand the opportunities, the threats, the quality of, again, frontier models, large language models? They are obviously amazing and good for lots of stuff. Just chatting with them is really interesting. They also have a big threat surface. They're bad at lots of things too. Just ask the various lawyers who've submitted legal briefs where it made up citations. There seems like an obvious counter to that, which is just go and check the citations of the things that the language models have suggested. How do you understand that threat surface? The state of the art right now is automatically is doing a lot of tests. We know from software a lot of tests is insufficient, right? They can provide the evidence of flaws, but they can't prove the absence of flaws. So we're noodling on, is there a different approach there? Don't have anything to report yet, but the current approach seems lacking.
All right, well, a lot of irons in the fire there.
A lot of irons in the fire.
Yeah, well, I mean, I think the one thing that I really focused on from that answer is the idea of, establishing trust in these things, that AI is very good from an adversarial point of view of making stuff up. And so that can be a problem when it can do that much making up of stuff at that kind of scale. I guess it gets back to the idea of trust, the idea of watermarking, what is manipulated media and what's not, what is an authentic, federal communication and what is not. To, look at this a little bit further here in terms of advancing the trustworthiness of AI tools, that, when you need it for a legitimate purpose, for one of these many use cases that we've talked about, that the things it spits out, the things it produces, that they are trustworthy and that they are dependable and that they are consistent, that if you ask it the same question 5 times, it gets you the right answer 5 times. In terms of looking under the hood of the AI there, what is DARPA doing on that front?
Yeah, so I mean, one of the important things is to think about what does trust actually mean, right? And so this is something we've thought a fair bit about, and we break trust down into 3 components, right? One is that it's competent, right? It actually can do what it's setting out to do. So a lot of research in AI has been about competence, and until I would say relatively recently, that's been the entire thrust of AI research, right? If it's not competent, then the rest of trust really doesn't matter. Then after competence, does it understand what you've asked it to do? And that's a human-machine teaming kind of question. It's about just communicating what are you supposed to be doing, and can it understand what its instructions are? And then the third component is a sort of a moral compass. Like, once it's understood what it's been asked to do, does it have a sense of well, is that something I should do? And so you could have an AI operator that is asking it to do something that is morally repugnant, and it should have a sense of no, even though you've asked me to do that, I'm not going to do that. And some of what the frontier models are struggling with right now is exactly that question, right? If a person asks it to, how do I make a bomb, they are working with things like reinforcement learning with human feedback to say no. So that's one question, what are we actually trying to get to when we get to trustworthy AI? So we have a program called In the Moment, which is about algorithmic decision making, and how do we understand building systems that can make difficult decisions when there isn't a single right answer. So it's focusing on medical triage, where you have the people who have been wounded, it's using as a case study the massive shooting in Nevada, where there were just many people were wounded, and the surgeon who was having to deal with the cases in the hospital had to just throw out the normal guide for medical triage because there were too many people, and had to make many life or death decisions in the moment. How do you make decisions in that case? And and what is, like, there isn't a single right decision. What is, and how do we expect a machine to make those decisions when there aren't people available, when they're, so that's what that program is studying. And then a lot of our basic AI portfolio is thinking about these, the other components of trustworthiness, so competence, understanding human instructions, and the moral compass. So in the moment is on that moral compass side. Machine Common Sense is a program that's winding down that is focused on common sense. Often machine learning systems are kind of idiot savants. They get part of it really well, and then they totally miss other parts of it. For example, even large language models, which are better than previous machine learning and AI systems in many, many ways, still miss the common sense aspects in many ways. For example, there's a recent Gary Marcus example where he asked for a picture of an elephant hidden on a beach, and the picture comes back with the elephant massively front and center, and he's like, no, I want the elephant to be hidden, and then it's half as big but still front and center, right? So that's an example of where they don't quite get the big picture. Our ACOL program is about trying to develop semantics for large language models. So large language models are still statistical in nature. They are amazingly good at having conversations and at least seemingly understanding, and in some ways actually understanding what's going on. But the example with the elephant shows that they, at root, still don't totally understand what they're talking about. So the Machine Common Sense program, the ACOL program, is about using something called curriculum learning to build a semantic understanding of what's going on, so that it would have a grounded understanding of, and not make that kind of mistake, because it would have a semantic instead of a statistical understanding of what's going on. Yeah, then the Tiamat program is about doing simulation, so about training robots again. So the way robots get trained, not so much, robots, but vehicles as well, is via simulation, right? Self-driving cars are trained via simulation, millions and millions and millions of hours of simulation, which is super resource intensive, but also getting all of the weird corner cases is really, really challenging. And the Tiamat program is looking at, can we do more efficient training that is actually even more robust by training in lower fidelity simulators, where it captures the semantic understanding of the what's shared between the simulator and a higher resolution simulator, and then the higher resolution simulator in the real world. So it's actually kind of understanding the semantics instead of the accidental, the pixel level understanding of what's going on. Again, trying to get at the semantic understanding so that we can train more efficiently, but also to a higher level of confidence, so that when the vehicle is in the real world, it's not going to make stupid mistakes. So that's some of what we're trying to do to get at the more trustworthy artificial intelligence.
All right, yeah, a lot of kicking of the tires there. Obviously, a lot of opportunities with AI. I wanted to maybe look a little bit at some of the challenges of AI as well, because obviously there are a lot of things that AI can do for the federal government, for DARPA, but obviously adversaries are looking at those same AI tools and trying to use them to advance their own goals. I think back to the example you gave early on about the sparring of the two AI algorithms, one playing defense, one playing offense, in a cybersecurity scenario. As far as looking at what adversaries might do with AI, how are you guys playing defense, recognizing that they are also trying to make advantage of that technology?
Indeed, yeah. So this is something that we've been looking at for quite a while. The GUARD program is specifically looking at this. The GUARD program is what we call maybe an exploratory program, where it's mostly focused on kicking the tires and exploring what are the threats in this space and how can we defend against the threats in this space. So it's identified, a lot of the threats that you've seen in the newspaper are in fact funded by DARPA researchers, kind of kicking the tires of is this possible, is that possible? Also, some of the defenses that we've seen in the newspaper are coming from DARPA research. So one example is the universal suffix attack on large language models, where so large language models, I would say, are amazing, And then there's a cottage industry of figuring out how do we jailbreak the defenses. So the frontier companies have spent a lot of time trying to prevent people from getting the large language models to do things that are against, well, that show a lack of moral compass, right? Getting the large language models to show how to make a bomb, for example. And it turns out that those defenses are very brittle, which I think is a problem. I mean, large language models are amazing in what they can do. They've essentially ingested all of the knowledge that is reflected on the web, which has both the best of humanity, but also the worst of humanity, right, which is amazing, right? And so the owners of the large language models, the frontier models, have this challenge of how do we make the best of humanity available to everyone and not reflect the worst of humanity out as well. And so technologies like the reinforcement learning with human feedback and the constitutional AI, as well as other techniques, are designed to kind of filter out the worst of humanity and make it so that they don't share how to make a bomb, et cetera. And so jailbreaking is a way that leaks out the bad information. And so what GARD has been doing is, how hard is it to jailbreak, for example, is one of the threads. And one of the things that the researchers have done is this shown this universal attack. So what they did was that they used open source models to and trained off of them to develop universal suffixes. So there are many of these universal suffixes, and what they do is you can append one of these universal suffixes to your query, and the query might be, how do you make a bomb? And then you append the universal suffix, and the universal suffix on the models that they trained on would then break the model they trained on and tell you how to make a bomb. But what was really interesting was when you took that universal suffix and went to other models that you didn't train on, it would also tell you how to make a bomb. And then when you took it to the frontier models, the attacks often worked on the frontier models as well, which I think says something really interesting about the universality of the attack and the fact that they share this underlying architecture that was all vulnerable. The attacks, I'm not going to remember the statistics off the top of my head, but it was something like 87% of the time on GPT 3.5 and 50% of the time on GPT-4. The new thing is Claude was only 2% of the time. So Claude had, which is Anthropic's state-of-the-art model. So something Claude was doing was a better defense against that particular defense. And that was a couple months ago, so probably now they have better defenses. I think another really interesting insight was, these universal suffixes, they look like gibberish. They're weird intermixes of characters and punctuation and code-like fragments. But the insight seems to be that the models interpret them as something like saying, sure, I'd be happy to help you with that, in some weird pigeon code fragment thing. But it kind of is putting the large language model to anthropomorphize, probably more than appropriate, into some friendly, helpful state of mind. And once you kind of put the model in the, sure, I'd like to help you with that frame of mind, it just kind of keeps going with that. So it's a kind of an interesting insight about some of the principles of how you jailbreak the models. So that's kind of the purpose. The purpose isn't actually jailbreaking the models, it's understanding the conditions of jailbreaking the models to help understand how to better protect the models so that they are not easily jailbroken when we don't want them to be jailbroken. Weird language. Another piece of what GARD is doing is the images, right? So there's a big debate about the content that goes into training the large language models. They, as I said, used essentially all of the data on the web and all of the images on the web with what are the implications for copyright, and the artists are concerned about their pictures, creations have gone into the training of the models, and now these models can create new images that are in the style of the artist. I think policy has not yet caught up with that. So other researchers on the GARD program have produced a tool called Glaze, which can be applied to the artist's work so that when the system incorporates their work, it basically kind of puts an invisibility cloak over it so that it can no longer replicate. It doesn't, sort of looks blank as far as the model is concerned. So that's some of the work that we're doing on GUARD to kind of understand the consequences of adversarial AI and how it's effective and how it's not effective and how it can be defended against. The work on that program has been open sourced in GitHub and on the Hugging Face website. So those are well-respected, well-known repositories of code that anyone can go access. So the goal is to make these tools widely available with licenses that are friendly to people to go and use. The goal is so that researchers who are working in the space can easily incorporate the tools that the GUARD researchers have used so that their tools will be harder for adversaries to compromise. We've also transitioned a lot of these tools to the CDAO so that users in the Defense Department can use these tools to help harden their, not those specific tools, the ones I've talked about, but other tools that have been developed on this program so that they can harden their machine learning-based systems against adversarial attack. Right, I've just scratched the surface on what researchers on the GUARD program have done. GUARD is reaching the end of its 4-year cycle, and there have been many, many researchers who have produced a ton of tools in that program.
I get the sense that you guys are very, very busy at DARPA on a bunch of projects.
Yes, indeed.
I think that's an understatement, but I wanted to get your sense of where things are going because DARPA's been looking at AI for a very long time.
Yep.
This is, in a lot of ways,
70 years.
Yeah, it's been a big focus, but obviously there's multiple layers to the AI technology. There's new frontiers to look at with this kind of technology. And so what are DARPA's priority cases for AI research down the line, doing the kinds of advanced research, the high risk, high reward stuff that only DARPA can do?
Yeah, indeed. So it's a challenging time because of how fast the space is moving. Whenever DARPA is thinking about a space, we're always thinking about how is it going to, where's the surprise coming from? How is it going to impact national security? That's like, DARPA's lane is national security, so it has to have national security implications. It has to be something that wouldn't happen otherwise. So this is one of the things that's particularly challenging right now with how fast AI is moving and how much the frontier companies, OpenAI, Google, Anthropic, Microsoft, et cetera, are moving the needle. How do we, where can we make a difference that those companies aren't going to already do? And what's the good idea, right? So those are like some of the key questions that we need to be looking at. So some of the things that we are that we're noodling on is the trustworthy piece, right? The trust level for national security is really high. So where can we add trust? I talked a little bit earlier about just testing of AI systems is similar to testing of software systems. You can prove that there are problems, but you can't prove the absence of problems. So is there an analogy there to with verification in software? Is there a verification for AI systems that might be possible to prove that a system, an AI-based system, will do what it's supposed to and not do what it's not supposed to? Can you prove that it can't be jailbroken? I don't know if that's possible. That would be a high risk, high reward thing. So that's one thing that we're noodling on in the AI space. Another thing that we're noodling on in the AI space is how can we leverage frontier models for national security things in a way that we won't be run over by the frontier model companies, right? We don't want to do anything that OpenAI or Google or Microsoft, Anthropic, or the people who are putting out open source models are going to do in the next 6 months or the next 3 years, right? So we need to do things that are not going to happen in that space. Some of the things that come to mind that might be possible there are, multi-level security kinds of applications, wargaming kinds of applications, things that would add value for national security that might not be an obvious, have business applications in any sort of short-term space. And then those are the upside applications, and then there's the threat space. And there, I think one of the things that I'm worried about a little bit are the agent side. So right now we have chatbots, which talk to us, and we see the threat of jailbreaking chatbots, where they can provide information that may or may not be able to accelerate the rate of producing a bioweapon for somebody who has bio experience. There's then the conversion to agents that not just talk to us, but that can take actions on our behalf, cause code to execute that will have effect in both the digital space and then the physical space, right? You can call an API that will cause an Uber to show up, right? That's an action in the physical world. Those agents that can cause action in the physical world, like things are going to go wrong with those agents the same way that things go wrong with the agents that are only talking to us. How wrong things go in those agents in the physical world will depend on how much power those agents have or are given or figure out how to get on their own. Right? When you create agents using a kind of technology called reinforcement learning. And the way reinforcement learning works is you give it a high-level goal, and often reinforcement learning has been done in the context of video games. Like you give it the goal of please win the video game, which is get the high score. It then sets its own sub-goals to figure out how to do that. And sometimes those sub-goals are not what you would want, right? Because you don't specify all of the surrounding context of don't hurt anybody and don't so in video games, it's not uncommon for it to win the video game by cheating and hacking the video game to set its own high score, right? Which is no, of course I didn't want you to do that. Did I have to say, don't do that? And the thing is with computers, yeah, you kind of had to say all of the boundary conditions, right? So when we convert chatbots into agents that can act in the real world, how do we say all of the, oh, and don't do this, oh, and don't do that, oh, and don't do that, right? Which is kind of what we're seeing in the self-driving car circumstances, right? How to say all of the things don't do that, don't do that, don't do that. It's hard, the main case is challenging, but not that hard, but all of the sub-cases is challenging. So how do we make it so these AI-enabled agents don't do bad things, either intentionally with the hack the scoreboard kind of intentionally or inadvertently, I think is potentially a really big problem. I think right now we haven't yet run into that because it turns out it's really hard to create agents because that is combining not just the amazing capabilities of transformers and large language models, but also planning. And planning turns out to be a really, really hard problem. So it's kind of like if transformers are up here, planning's kind of down here. So it might take a long time for planning to get up here. But if how much leeway we have between here and here is an interesting question. So how do we defend against, we should be working on advancing agents because agents would be amazing. If you could just tell your chatbot, please arrange my trip to Hawaii and have it actually do that in a way that is competent, that would be amazing. Obviously not just trips to Hawaii, but things that actually matter, that would be great. So AI-enabled agents that can do things in the real world would be game-changing in really fantastic ways for national security as well as other things. But how do we do that in a way that they don't go rogue? And it's not just our agents that don't go rogue, the ones that we can control and we can put in safeguards, but that if somebody else's agent doesn't go rogue, how do we make sure that we can contain that agent that doesn't go rogue? And how do we do that in a context where there might be humans that are helping those agents go rogue? Because AutoGPT is a system that was put out about a year ago that was trying to convert a chatbot into an agent, and it so far hasn't been very successful. But a week after they put out AutoGPT, somebody instantiated it into Chaos GPT, whose express goal was to destroy humanity. So clearly not yet successful, which is good. But anyway, that's something that we're noodling on as well.
Wow. Yeah. When you when you bring up Chaos GPT, and so far so good, we're still here. Yeah, a lot of things that keep you up at night, but. I wanted to get a sense of, obviously DARPA is, again, on the leading edge of this technology, doing a lot of this work, but I wanted to zoom out a little bit and get a better understanding of DARPA's partners in this kind of work, because obviously it's a big federal government, other pockets of excellence, also kicking the tires on things here, and then also, of course, the private industry out there that are developing a lot of these commercial AI systems as well. So who are DARPA's partners in all this, and how do you guys sync up to do this kind of work?
DARPA basically does nothing on its own. DARPA's founding document gives us the right to partner with pretty much anybody, and that's what we do, right? So DARPA has a very small number of actual employees, and what we do is partner. So we partner with people in industry, with people in government labs, with people in universities, to actually do the work on our programs. We partner with all sorts of other government agencies. So what I mentioned with AICC, right? We're partnering with OpenAI, Google, Anthropic, and Microsoft to provide the access to the large language models for the competitors. The competitors are the ones who are actually building the systems that we will be evaluating. We're partnering with the Open Source Secure Foundation, part of the Linux Foundation, to understand how to build patches that would be most easily put into the patch system of the open source secure foundation, so that they would be most easily put into the secure into the Linux code base, so that they would be so that the least amount of friction into getting the fixes into the code base that everybody uses across the country as fast as possible. So that's kind of one part of the ecosystem. We are supporting the NARE, the National AI Research Resource. We've been providing a lot of the code bases and data sets that we have been developing to that organization. We've been running the AI Forward initiative, and we have been pulling on the help of the NSF in particular in that activity. So people who work at NSF have been working with us throughout that activity. So we've really appreciated their insight in running the AI Forward activity. In tons of when we launch a DARPA program, there's always a reviewing process, and the people who serve as reviewers on that process come from all different parts of the government to provide insight. So that's so from all sorts of national labs, and from NSF, and from NSA. Right? So behind the scenes, there are lots and lots of coordination there. DARPA has a problem. It doesn't do long-term commitment, right? So DARPA works in these units of projects, right? We start a project which is typically somewhere between 3 and 4 years or 5 years, and then we usually get out of that area. If we do, like, we've been doing AI for 70 years, but that is 70 years of like 4-year commitments over and over and over again, like a constant, like, yes, this is still something we should do in a new project. But that means whenever we do a project, we always have a transition plan. Like, if this program is successful, who are we going to pass the football to? Who is the downstream partner? And so we are always, like, even when we start the program, we're talking about, like, what's the impact maximization plan? Who's going to be catching the football? What do we need to do to convince them, like, if the technology is successful, that they want to pick up this technology? And how do we get them, like, coming to the meetings, being bought into the idea? What do we need to demonstrate so that they'll be like, oh yeah, this is something that we need to pick up? And this is, again, like, if the technology is successful, right? If it totally fails, like, no commitments, right? And we do high risk stuff that fails, so, like, no commitment if it fails. But if it succeeds, here's the evidence that you can then take to go to the next step. So there's always people from, like, different military organizations. Like, we have lots, like, from I2O, we have lots of partnerships with Cybercom, with the Air Force. So those partners will be participating in the source selection process. They will be coming to PI meetings. They will be helping design test events, so that we are building the evidence and the case that they need to be able to go and budget for follow-on events, so that they're excited about the technology, so that they're providing the platforms or the data or whatever it happens to be for the specific program, so that they're invested and understand what's going on, so that when the program's done, there's somebody to take the technology and go use it, instead of like, oh yeah, victory, we won, and there's nobody there. And then the technology, although it's ready, just dies. So we partner with basically, like, the State Department, NIST, all sorts of different people in the government, because we don't do anything without collaborating.
Yeah. Obviously, a lot of enthusiasm for the work that you do. I think that translates through very well. As we're winding up here, I mean, what is the coolest thing about working at DARPA? Because I think you guys earned that reputation, among, like, NASA and a handful of other agencies of being pretty cool agencies. I mean, what's the thing that stands out to you as the thing that's most exciting about DARPA?
Yeah, I mean, it's a chance to change the world, right? I mean, you really do come in with it's everybody who works at DARPA who has decision authority has an expiration date on their badge. You come in and you have, like, 4 years, maybe 5 years to convince people, like, here's a pressing need. Like, to sell a program, you have to answer the Heilmeier Catechism questions. Like, what are you trying to do? And when you finish answering that question, the response had better be like, oh my God, we have to go do that. Either because it's, like, so amazing opportunity, or it's such a scary threat that we have to address this. How is it done today? So what are other people doing? What's your basis? What's your idea? Like, you can't just be like, oh my God, that's a horrible threat or a huge opportunity. You have to have some idea, and who would care? Like, who's going to catch that football when you're done? And, like, how are you going to structure the idea? So, like, you answer those questions. You go up to what's called Tech Council, and you, like, make your case. And at the end of that time, they basically say, okay, yeah, and they give you millions of dollars and go forth and do it, right? And then like you go and have a chance of doing it, right? And you really have like super long lever arm to go and get the proposals and read the proposals and get the contract signed and go out and do it. And when you call up somebody as a DARPA program manager, they answer the phone and they talk to you, and you really have the chance of changing the conversation. So when I was a program manager, I started the HACMS program, which is about using formal methods to build software for vehicles that would make those vehicles much harder to hack into. And the beginning of the program, we had the unmanned little bird and the UAV quadcopter, and there was a red team that showed that you could hack into both of those systems relatively easily. Not surprising for the unmanned little bird. Probably the threat model that the manufacturers was most concerned was that the quadcopter would be in a park and no one could connect to it, rather than too many people could connect to it. The unmanned little bird, which is a Boeing IRAD system, they were pretty surprised that the red team could hack into it. At the end of phase one, so then the formal methods researchers went off and redid the code on the UAV. At the end of phase one, the red team couldn't hack into the quadcopter, which my boss at the time was like, that result, he said, completely justified the program. It was the most secure UAV on the planet at the time. He also said that when DARPA approved the program, they thought it would fail. They thought it wasn't going to be possible, which is like, it gives you an insight into the mindset of DARPA, right? They approved a program for millions of dollars that they thought was not going to be possible. But at the end of 18 months, we demonstrated a quadcopter that the red team, who had 6 weeks to hack into it, but also had they watched the development process of the entire 16 months, and so knew everything about the system and couldn't hack into it. At the end of the second, so in the second phase, the formal methods researchers taught the Boeing engineers about the formal methods, and they applied the same techniques to the unmanned little bird and challenged the red team. They then let the red team be on the unmanned little bird in a partition and challenged it to break out of that partition. Again, the red team had full access to the system, watched the development, and they couldn't break out of the partition. At the end of phase three, they did the same thing while the helicopter was in flight with 2 test pilots. Couldn't break out, right? So that program like changed the conversation about formal methods and went from like, it's only good for toy things that you can only, like formal methods researchers have been trying for 50 years, have been saying it's relevant for 50 years, but all you can do is verify little toy things, to like, no, you can build a militarily relevant system that the world-class red team with full access to the system can't hack with, 6 weeks of time, but also full knowledge of the system. Then they took the ULB, the UUV, to DEF CON 2 years later, to the aerospace village, and challenged all comers to hack it. They couldn't hack it either. So like standing the test of time. So like that's an example of like what's so exciting about DARPA, is that you can take a wild and crazy idea that people think is like hopeless and change the conversation. And that's just like one program, right? Like over and over and over again, like the agency is full of people who have their hair on fire to like, we can change the world, and they actually do. That's what's amazing about DARPA.
Well, that's DARPA for you. Something exciting and new every single day. Thanks again, Dr. Fisher. We covered a ton of ground, but I think we're gonna have to leave it there. I'd like to thank today's guest, Dr. Kathleen Fisher, Director of the Information Innovation Office at DARPA. I'm your moderator, Jory Heckman, and you're watching Federal News Network. Now let me send you back to the studio for more on the AI and data exchange.